All right, you guys, I am going to attempt to make this little video for you. I'm going to chunk it into two separate videos. So the first thing I want to do is I want to talk about integrals whose answers are inverse trig functions. Now, I know you're thinking there's 6 trig functions. There's so many I have to worry about. You really only have to worry about 2 formats, okay? The first one is the inverse sine, and it's always going to take this form. It's going to have a square root in the denominator, and it's going to have the difference of 2 perfect squares under the square root sign. And then the stuff after the equal sign is just like a formula that you plug stuff into. And then, of course, I have an example over here, but I'm going to write some examples out. You can come back and look at the example yourself, or you can pause it and watch, or look at what the example is. The second one is the inverse tangent. Okay, and now the inverse tangent has the sum of 2 squares in the denominator and no square root. So if you see a square root in the denominator and it's a difference of 2 perfect squares, it's probably an inverse sine problem. If you see the sum of 2 perfect squares in the denominator with no square root, it's probably an inverse tangent problem. Okay, and then here's an example. Again, you can pause it, look at the example, see if you can figure it out, or you can come back and look to it later. I want to do 4 examples with you, though. So let's take a look at the first one here. This is saying the integral of 1 over 4 minus x squared. I see the square root in the denominator, so right away I'm thinking this might be an inverse sine problem. I see a subtraction, and I see 2 perfect squares. So again, I just want to remind you, 2 perfect squares, their difference. And that's what I have going on here. So the first thing you want to do is you want to figure out what your A and your U are. So again, if you look back up at that formula, it's kind of getting junky here. So let me erase all this stuff here. We have an A squared minus U squared. So in this case, our A is 2 and our U is X. So that means that I could rewrite this integral as 1 over the square root of A squared, 2 squared, which is 4, minus U squared, which is X squared, and that's what I have. Now, as with all U substitutions, you do have to worry about taking the derivative. So the derivative of X is 1, so I get 1 dx on this side, and then that's going to take the place of the dx. I'm going to put my du in here. Okay, I'm going to zoom back out because it's making my marker really fat. Actually, I think I can adjust that here. Okay. So then if I know my A value and I know my U value, I can just plug it right into the template for the inverse sine. That says the inverse sine of U divided by A plus C. So I get the inverse sine of U, which is X, divided by A, which is 2, plus C. And that's it. That's the answer. Nothing crazy going on. Okay, switch up colors here. I'm going to go to purple for this one. Number 2 has a little bit more going on. Remember, any constants that are multiplied in, I can pull them out in front. So I'm going to rewrite this as 3 times the integral of x divided by the square root. There's that square root that kind of tells me that it might be an inverse sine. 25 minus x to the 4th dx. All right, I got a difference in the square root, and it's 2 perfect squares on either side of it. So again, I'm going to figure out what my A is. I'm going to figure out what my U is, and I'm going to take my derivative of U. Okay, so in this case, I'm looking at the 25 to figure out my A. So if A squared is 25, that means that A is 5. I'm looking at the x to the 4th for my U. So if U squared is x to the 4th, then that means that U is x squared, because x squared times x squared is x to the 4th. And my derivative of U is 2x dx. Okay, so if you notice, all my leftover stuff is just a dx. So we're going to have to resolve that 2. And I'm going to do that by dividing out the 2 and getting that 1/2 du is equal to x dx. Okay, so now I need to rewrite this integral. I already have my 3 out in front. I'm going to pull out the 1/2 that I resolved in my du. Integral, the x dx is going to be absorbed by the du, so I'm just going to have a du at the end. So I'm going to put in 1 over the square root of a squared minus u squared du. And now it fits the inverse sine template. So on the outside, 3 times a half is 3 halves. Inverse sine of u divided by a. U is x squared. A is 5 plus c. And that is the answer to that integral. Okay, I think the next one is an inverse tangent problem. Oh, and I know that because there's no square root and it's the sum of two perfect squares. So I just want to remind you that if you have the integral, let me write up here, integral of 1 over a squared plus u squared dx du, that's 1 over a inverse tangent of u over a plus c. I had to kind of cram that in there, but it's at the top. It's at the beginning of the recording at the top of my notes. So again, I'm going to figure out what my a and u are. So I'm going to let a equal 1, because if a squared is 1, then a is 1. I'm going to let u equal 3x. And I got that by looking at the 9x squared. So if u squared is 9x squared, then u has to be its square root, which would be 3x. And like always, I have to take my derivative of u. So I get 3 dx. I have a 4 here that I'm going to pull out in front, and I have to resolve this 3. So I'm going to get 1/3 du is equal to dx. And now I can rewrite this integral. So I'm going to pull that 4 out in front. I have the 1/3 that I'm going to pull out in front. The integral of 1 over, because I pulled the 4 out, 1 plus 9 squared is really a squared plus u squared. And then my dx is resolved with the du. So now all I have left is to apply this formula. So the 4/3 out in front is there. I have to multiply by 1 over a, which a is 1 in this case, inverse tangent of u over a, so 3x divided by 1 plus c. And then, of course, I got a lot of divide by 1s in there that I'm going to clean up. So 4/3 times 1 is 4/3. Inverse tangent, 3x divided by 1 is 3x plus c. Okay, and remember, if I'm talking too fast, you can always slow down my speed in the recording. And if you need to pause to kind of catch up and write down what I'm writing, you can pause and then keep going with it once you're ready to go. All right, last inverse tangent problem. What color? I'm going to go with red for this one. All right, so this one, I got stuff flipped around, but that's okay because with addition, you're allowed to change the order. So you could really think of this as 16 plus x to the 4th, but I'm just going to leave it as x to the 4th plus 16, just to make my life a little bit easier. So again, I have to figure out my a and my u. So my a comes from the 16. If a squared is 16, then that means that a is 4. My u comes from the x to the 4th. So if u squared is x to the 4th, then u is x squared. And I'm going to take my derivative of u. I'm going to get 2x dx. But again, I don't have a 1/2 floating around in that integral, so I'm going to resolve that, or that 2. I don't have a 2 floating around in the integral. I'm going to resolve it by multiplying by 1/2. And I get 1/2 du is equal to dx. So now I'm going to rewrite this integral. I'm going to pull my 1/2 out in front from my du. The x dx is getting replaced with the du, so I'm going to put that at the end. I need a placeholder up here for that x. I kind of covered it up there. And then my x to the 4th plus 16 is my u squared plus a squared. And I know that that's in the wrong order. It's a squared plus u squared. But like I said, because it's addition, I can reverse the order. It's not going to change my problem. So my final answer here is going to be 1/2 times 1 over a. A is 4. Inverse tangent of u over a, so x squared over 4 plus c. And then I'm just going to clean it up. 1/8 inverse tangent of x squared over 4. You can write that as 1/4 x squared if you want, plus c. Okay? And I'm going to end there. I was going to try and do 7 examples here, but I'm going to do 4 examples in this video, and I'm going to do 3 examples in the next video. So come back for some more. And my lights just went off. So let me